Welcome to the webinar of today in WebLearn. Today's topic will be on rheocasting for chassis components in aluminium, which will be interesting to listen on. And we think this is our 25th or 26th webinar in the full series, WebLearn series, that has soon been going on for 1.5 years and will continue at least a year out. Hopefully we can continue further on as well. And next, please, Anders. Here you see the registrants of today. Maybe the late ones aren't on the list. So there is quite an extensive participant list from various places. And you can take the next as well. And as I just say, our WebLearn series, which is funded by the KK Foundation due to the COVID-19 crisis, to help to provide competence development for companies to prepare them better once we come out of this crisis. And me talking, you can take the next one, is the person to the left, Stefan Berlin, one of the project managers of the WebLearn project. And later on, you will meet my colleague, Madeleine Zetterlind, which you also both have seen and heard so far as well. But the most important persons of today are the presenters, of course. Professor Anders Jarfors from the School of Engineering, who will start presenting, and then also our guest, our honorary doctor since half a year back, Per Jansson, who will both talk on the subject, which will relate to the reason for Per's doctorship as well, I guess. And the agenda for today is the short introduction just now, and then Anders will begin the presentations, and then we will turn over to Per, and then there will be a panel discussion, and we will wrap up in 1.5 hours. So please stay with us all the time. And the format that for the webinar, the next slide, please. It will be recorded, the webinar, except for the panel discussion, and you will have access to the recording afterward as well. So please have your microphones turned off during the presentations and cameras, unless you want to be seen. But during the panel discussions, please turn on your cameras and take an active part in our discussions, since those are an important part of the webinar. And if you are unfamiliar with Zoom, you can, thank you. You have down to the left, you have the mute for the microphone on and off, and also the camera on and off. And a bit to the right, you have the chat function, which open a chat box. And please also take the opportunity to write questions during the presentations in the chat box, and we will address those questions in the panel discussions so you don't forget it. So once again, a warm welcome to everyone. And with that, I hand over to Anders. Thank you.
Thank you very much, Stefan and Madeleine. Well, the topic of today is on the potential use of rheocast aluminium alloys for vehicle chassis components. And this is based on a project called Rheca, which was funded by Vinnova. And our partners here were, well, Comtech was one of our partners, and then we had Scania and Volvo Car Corporation as well as part of industrial support companies. It was also a collaboration between Jönköping University and the Royal Institute of Technology in Stockholm as well. So that means it's a rather wide collaboration. Now, when you start something like this, the world is constantly in flux. And there were some rather large changes in the casting industry in the recent few years. One thing that happens is that when you look at the car body, you have a new type of driveline that comes into large scale. You have a battery area, and then you have the rear and the front of the car. And the big change that has taken place is that casting has been replacing many parts in the rear and in the front here. So there's single piece manufacturing instead of maybe having 70 to 100 pieces that are being joined together. And that means it's some rather dramatic changes. One thing is, of course, the choice of alloys. The other part is the design and the ability to fabricate larger castings and how to do that. There is also another big challenge, and in fact, in order to cast something which is actually this type of casting, that is the rear you see here, is that the machines are extremely large. And when Tesla started, there are no such large machines. And this has changed during the course of the project. And has taken real speed, and that has also naturally affected both the start and the end of the project. So what are we going to talk about today? Well, first of all, we're going to, as I show here, we're going to talk about the situation. We will talk a little bit about the material sustainability. We'll talk a little bit also about how you can affect fatigue and crash safety. I will show you some brief results from the study itself, and then some conclusions and a little bit of a future outlook in the part that I'm presenting. Now, there are several things that are up on the board. It's not just material properties. It is also sustainability that comes into play. And to the right, you can see the carbon dioxide equivalents emitted during the production and use of a car. And this is from a life cycle assessment. And it's the XC40 compared to the Polestar cars. And as you can see, the gray area here, that is the manufacturing load that comes into the car, and the orange here is the energy usage, and this is an internal combustion engine. If you turn over to electric drives, you have an addition which corresponds to about 50,000 kilometers, and that is the emissions from the battery manufacturing. And the greener electricity you get, the lower the use phase in carbon emission comes. And this is actually quite interesting, because the thing that happens is that the only carbon dioxide emissions in the end, essentially the only, will reside within the manufacturing phase. So looking at the Paris Climate Accord, going beyond that, it's not enough just to change your energy mix. You also need to take a look at how you do your manufacturing part. And a lot of bits in this lies in the use of primary and secondary material. And therefore, there's a lot of questions related to the manufacturing that comes up when we start talking about sustainability. So for the long-term carbon footprint, it's about the material choice, what material type we should use, and what the source of the raw materials for that material type is. And that also, of course, involves the right choice of process route. So that is one of the foundations. The main thing that happens also here is that because of this, we have a change in driveline. So that means that the nature of the products being produced will change. Internal combustion engines will no longer be dominant. And that means that the material mix will be different. And then we have circularity. We need to see how the materials can be recycled. And of course, the driveline is one part, and then you have the body in white. And the body in white is something which will be more into focus here today, because we are talking about larger functionally integrated castings. and issues that sort of are related to this. If you look at the material used today, then you have a lot of sheet and extrusions in the material, and these have generally lower silicon content. And the interesting part here, if you look at the rear of the car, you have 100 parts in that. And that might constitute, say, 4 or 5 different alloys and many procurement processes and many processes related to joining, and also a lot of tools. Now, changing into single casting means that the material mix will change. The number of procurement processes will be reduced, and the material usage will be modified, so to say. So there's only one material in the back, and that is actually conducive to circularity because you don't have issues with contamination between different material kinds. You have only one material in the back, maybe not 4 or 5 or 6 or 7 materials, only one. And it's a reduced number of joinings. You don't have contamination from rivets and bolts and things like that that comes into material items. It's actually making sustainability more easy. And then there's, of course, the challenge of casting things lighter. And Rheocasting is one of the means we have in order to cast more thin wall components in order to create a green and fruitful future here. Now, Rheocasting as a process, the whole idea is to reduce the heat content in the material before you cast it, and also to provide some particular flow properties. So it should be shear thinning, and it should keep turbulence to a minimum. And there are essentially 3 different routes. We have fixer processing. That means that you reheat and you remelt something. And this is typical fixer molding, which is used in magnesium materials. And then we have rheoprocessing on the other side, which is a process where you cool down and you allow it to solidify. And a lot of the processes today, like the GIS and the seed process, it's a new Rheocasting process, are found here. And what we've been working with, and you will see more about that, is the rheometal process, which actually has an element that is being reheated and an element which is being just cooled down. So it's a mix of 2 materials. And therefore we call that a little bit of a hybrid process here. All of these processes, as I said, they serve the purpose of reducing the heat input primarily. And when you look at the reduction of heat load, thermal load, that means that the first thing that happens is that die life goes up. So you get better die economy. And then you need to use less release agent. And this is actually something which is very, very important, because what drives defects is actually release agent emissions and atmosphere generated in the tool. And this is actually very, very important when you're going to cast larger components. So this is a process issue that we need to work with. And that is something that is critical to what we are working with. Another benefit of reducing the die spray is that cycle time is being reduced because the spray cycle is going down. And that is also a critical element. What has been seen also is that you have significant scrap reduction at the casting station because of the fact that you actually have less porosity and less issues with the release agent. And that means that what we can talk about in terms of productivity, since one of the benefits is that you have to use lower silicon alloys. That means that we're moving into alloys that normally are seen in gravity die casting or low pressure die casting. And that means that we can offer something that is in the, a productivity which is like high pressure die casting, but with alloys and quality, which is similar to gravity die casting processes. And then you have the thin wall capacity, which is also important when it comes to weight reduction. And this is due to the fact that we have a shear thinning behavior in the material. And the shear thinning behavior allows you better to manage transitions from thick to thin sections. And because you have reduction of porosity, primarily because of the reduction of release agent, and that you have a partial solidification, you get weldability and heat treatability as cream on top. So Europe is one of the areas where these processes are growing, but it's foremost growing in Asia and in manufacturing there. So if you look at the Rheocast components that are now out and being used, it's, for instance, knuckles. This is in production and used in cars. We have shock towers. This is a BMW shock tower, which is being road tested at the moment. And this is produced, both these are produced by a company called Silver Bases in China. And what you can see is that, first of all, you get good productivity. What you get is that you can actually utilize the better ductility in to have a weight reduction. And cab mounts that are in production in China have shown that you have 59 to 68% in weight reductions. And then under introduction, you have connecting rods, main bearing caps, knuckles, control arms with weight reductions in the order of 10 to 56%. And bench testing has all been passed by the components that I'm mentioning here, and some of them are in production and some of them are under road testing. In Sweden, we have essentially been successful in producing truck components. That is the main success here in Sweden, and we're working to see if we can get applications in the car industry. And of course, then the mega casting by Tesla has put us on high alert here. So if you look at it, the Rheo metal process that we're working with, then you take the metal, you team off about 7% of the melt, and then you have a cassette where you have 6 of these in cooling, and you stir it into the ladle. So you reintroduce the 7% you just teamed off, but has been cast in the previous cycle. And then previously we were just pouring that slurry, but we saw that there were some issues in this, and we added on a second step. And a lot of the work that we've been doing now is to understand the consequences of this second step. And that is the type of results that I will show you here today. And it has some rather significant consequences. Now, what we saw that when we look at the static material properties, we have, of course, the high pressure die casting ratio or standard, so to say, that is 1. And when we have the single stir, we did not always get a property increase. But with a double stir, we had about the same properties. What was different was that we had a change in the ultimate tensile strength. So we had a slight reduction when it comes to single stir, but with the double stir, we had a significant increase in properties. And of course, as you know, materials harden during deformation, and of course, there must be some changes in elongation as well. Now, what you get, as you can see here, with the single stir, we had a slight reduction in yield strength. And that is also a consequence on how the material actually solidifies. And if you get something which is softer, you also have something which has a little bit of a better elongation. But what we managed to do with the additional stir was to recover that strength without loss of elongation. Actually, what we got was an improvement of elongation in this. So we could expand the elongation by 50% by doing the double stir as at the maximum, so to say. Now, one thing that was up for discussion is also porosity. As you know, when you talk about porosity in commercial size materials, you have relatively large porosity level. And in this case, it was a full-scale large component. And with the single stir process, we had up to 6% porosity in the regions that we were investigating. And we also looked at the pore numbers, so the number of pores per unit area here. Now, when we did the double stir, we actually didn't really change the number of pores, but we significantly reduced the overall porosity. And this is, of course, not surprising, because when you look at the extension here, if you halve the porosity, then of course you get better elongation. Then we also did fatigue testing, and this was push and pull fatigue testing at 150 degrees centigrade, which was corresponding to what this type of component we had as a target was supposed to endure. And the high pressure die casting managed about 60 megapascals, while we got an increase with the semi-solid processed materials. And what we did was we used the staircase principle in order to establish the fatigue strength level here. Now, one thing which is important here is to say that there is not really any change between the semi-solid material with a single or a double stir. And this is, as you can see, the variation you see here. You have a reduction in porosity, so you have half the porosity. But it did not really affect the fatigue performance. And this is something which is still under debate for us, but it's definitely so that the defects here are not pore driven. So there are some other defects that we need to manage here, and this is where our research is continuing. When we looked at the pore size and the pore size distribution, we saw that we had a slightly reduced amount of the larger pores. So all the pores became smaller. But since it did not significantly affect in the semi-solid process, the reduced porosity did not significantly affect the fatigue life. There are other elements here that we need to look at. When you focus on this, what we can say here is that the fatigue strength definitely was 70 megapascals and was comparable between the two processes. Now, what we could see is that defects initiated in similar locations, and there were cracks with crack area, crack sizes about 1100 micrometers. And we'd also, in the stirring process, since this did not significantly influence the fatigue life in this, we could say that the double stir process did not influence the number of pores. So that means that we did not really introduce more defects by stirring a second time. But the issue is still that even though shrinkage was significantly reduced, we did not strongly affect the fatigue life. Now, so what we saw here, that oxides are probably oxide content is similar for the two processes, but we need to work more on how to actually manage filling and such. And this comes as a rather important part, because if you look towards the future, so one thing that we could see is that we could have a better elongation, especially if you have slightly lower yield strength requirements. And that means that what you can work here is the low-hanging fruit, and you can go directly for process optimization, and you can start working with body-in-white type of components. When it comes to high strength performance and high performance parts, there is likely to need further alloy development. It's since we can have better elongations, we can actually have better crash performance, even if you have a slightly higher strength of the materials. Now, the thing which is important to realize here is that the first part which is taking place here is that you need to understand how to design for large casting and functional integration. And the strength of material is primarily alloy driven. So if you want to have a strong material, you need to work on the choice of alloy or alloy selection. While things like the elongation and the fatigue strength is primarily something which is process driven. And with that, I would like to thank you for listening, and we should move on. So Madeleine.
Yeah, thank you very much, Anders, for this nice presentation. We have actually a question in the chat, so I will read it for you, from Johan Dahlström. Sustainability, what is standard deviation for CII02?
Oh, the standard deviation, I don't know on that one. Sorry, Johan. But I can share the report with you if you want.
Okay.
Thank you.
Good. So I don't think there are any other questions right now. Yeah, one more question. What is the difference between the single and double stirring?
Oh, well, the single stir is essentially only when you create the slurry and you allow the metal piece to cool down the melt and form the slurry. The second stirring is something that we call melt activation. So that means that we condition the solid particles in the slurry by a second stirring stage. And there is no melting taking place in that step. It's essentially only a mixing and shearing operation where we prepare the melt to have the right shear thinning behavior and the right yield strength, because the slurries that we are talking about have a strength as well. They do not flow automatically. They need to have a certain shear level before they actually start to flow. And this is very, very important when it comes to die filling behavior.
Okay, and here is another one. Oh, coming in at high speed. Let me see. Prolonging the first stirring would not be a solution then?
Well, the first stirring does not give you any additional shear when you have just a small pin after the fact that the metal, the aluminium lump has dissolved. So that does not give you a strong effect. We have tried to have an integrated impeller into the first stirring part. But experiments on larger scale actually shows that it's more efficient to reintroduce another impeller and stir. And that is actually how the process is looking today.
Okay, and we have one more question from Diraya saying, is there a significant difference in the microstructure between single and double?
Not really not on the microstructural level, but it is on the macro level, because you get regions which are more densely packed if you do not shear the material sufficiently, and that means that you can get a lumpy flow, and that increases the risk of phase separation during the initial filling. So you get the squirting in the liquid phase instead of having all the particles entering at the same time.
Okay, and the last one, and then we will move on from Torbjörn. What type of stirring technology is used?
Oh, well, the first, it's well, you can see it as a normal drill, and you just insert a rotating body, and it dissolves, and the shearing on that cylinder is the first phase stirring. The second phase stirring is a two-blade stirrer, because the two-blade stirrer maximizes the shearing in the melt. So it's a similar mixing process as you use in powder metallurgy, for instance, in order to break agglomeration in metal powders.
Good. So thank you very much. Good questions. And we will, after Per's presentation, we will continue the discussion. So please collect more and think about more questions to discuss. But now first we will let Per Jansson on stage. Please, Per.
Hello. Thank you, Madeleine. Yes, I'm going to talk a little bit more on the practical level, the foundry perspective to transition into Rheocasting from, let's say, a conventional liquid high pressure die casting process. So Anders. Yeah, and we have these different equipment to consider. I mean, we first have the die casting machine. We have the furnace, how you handle your melt. And then you have the different alloys. We have the die and the design of the die. Then we have the part design. Then we have training or education. And then we have some commercial thoughts and new segments that will be brought into the foundry with this technology. So, yeah, the die casting machines. First of all, you need to look in the size of die casting machine. Today, I mean, if you have a conventional high pressure die casting machine, you have the projected surface of your shot versus the metal pressure you're going to apply on that surface. And that gives you an opening force, and then that dimension, what size of die casting machine you are using. What we have learned is that when you do this calculation, you can apply a factor of approximately 0.65 and still are able to cast those parts in that same locking force machine. This is, of course, also in somewhat also geometry driven. So, but in general, 0.65 is safe to calculate. Another thing that this then brings to the die casting machine is actually the shot end, because it have shown that we can cast much higher shot weights in small machines, and then you have to ensure that you can apply such a large plunger in the machine, so you are able to inject the amount of material needed. So one cannot only look at the locking force, one have to think a little bit on the injection side as well. Then we have the velocity, and the velocity of the metal or the piston, so to say. If we talk about thin wall castings, we see that we use a higher velocity, similar type of shots that you find in a conventional high pressure die casting shot. But in thick wall components, it's very important that the machine can handle very low velocities, which is not common to use in conventional high pressure die casting. And as I said, the shot sleeve, the material does not behave in the same way as you pour in a liquid metal, where the metal runs all the way up to the parting line of the die. It doesn't behave like that when you pour in a slurry, because it's like more people that lives up here in Sweden have shoveled snow, and you put the shovel in the snow and you start walking. It's like the snow is traveling towards you and not away from you. And the slurry behaves a little bit like that when you start to move the piston, that the material travels towards the piston and not away for it. And this then give us that we cannot have too high filling rate, because then the risk is that the material pops back out from the filling hole. So larger piston diameters in some cases is needed here. We can see that we use the same piston systems that we use in conventional high pressure die casting, both solid and piston with rings can be used. So that's no difference. I also would like to say that the shot sleeves that we are using is the same material and same type of shot sleeves that we use for conventional high pressure die castings. Then we come to the piston lubrication. We use the same types as we use for conventional high pressure die casting, so no change here. But we have seen that when we tore these high loaded components, that the amount of lubrication that you apply is important, so we don't take the piston lubrication into the cavities, and therefore we would recommend that you use a lubrication system that lubricates on the return stroke of the piston instead of that you pour it on the piston, so to say. Vacuum, that's also Rheocasting benefits from using vacuum in the same way as conventional high pressure die casting. So if you are equipped with that, you can use that. And then if we take the maintenance routines, I mean, there's no difference between Rheocasting and high pressure die casting, so to say, regarding the die casting machine. Then we come to the furnace. All type of furnaces can be used. We have seen an advantage to use crucible furnaces, depending on that we have quite a lot of room in these crucible furnaces for the slurry making and the casting of the EM. The system is also compatible with conventional dosing furnaces that you find on the market. It's also depending a little bit on how you handle your melt. Do you have central melting, or do you melt by the machine and so on? So you have to take that into account. We have seen that with central melting system, we have less variation in temperatures. Temperature is in general of the liquid part is very important. If we have central melting, it's easier to clean and degas the melt. It goes the same way with conventional high pressure die casting. If you're melting in the furnace by the machine, it's very important that you have enough capacity in the furnace, so you can avoid the temperature fluctuations. And then of course cleaning is more difficult when you melt at the die casting machine in the furnace. Temperature stability, we have shown that a tolerance of 20 degrees, we are able to keep a very stable process and a slurry. So people that think that it's very important to keep the metal at the same degree or very low, that's not really true. We have a width of around 20 degrees. If you melt at the furnace, we see that charging of the furnace is important. I mean, if you lift out, let's say for instance 10 kilos in each shot, it's important that you add 10 kilos also. So you don't cast for 1 hour and then you need to add the whole amount that you have taken out. Then that's bound to give you problems in temperature fluctuations. So that's something that need to be considered if you have that system in place. Then we have one advantage with this is that you have in the same installation you can cast both with Rheocasting, and you can also cast conventional liquid casting, conventional high pressure die casting. So one thing that is important is that you need them to switch the alloy between the two processes. Usually in high pressure die casting, you are using eutectic alloys, and in Rheocasting we cannot use the eutectic alloys, and therefore you need to change the alloy. And one solution then is that you can keep the conventional high pressure die casting melt handling on one side of the shot end, and on the other side of the shot end you implement the Rheo process, including also metal handling for that type of alloy. Depending, of course, how many changeovers you're going to do, I would say the extra investment of another furnace might pay off due to, otherwise you will have long setting times in between the two processes. Maintenance routines, I would say, is the same. It's important that you clean out the furnaces and scrape if you have a thermos type of furnace, so you don't get oxides and things like that in the furnaces. Yep. The alloys then. This is probably the biggest change if you compare conventional high-pressure die-casted parts, which are usually eutectic alloys. I would say between 9 and 12% of silicon, right in the middle here. That means that we have a very low process window of making the slurry, because we live on the distance from the liquidus line down to the solidus line. And here we would like to have a long distance compared to that we get with the high pressure die casting alloys. What's important when you do Rheocasting is that you make thermal analysis to establish where you have your liquidus lines, liquidus temperature. And then when you set up the process, that you set the superheat in relation to the fraction solid that you need, so you get a very stable process. You need then to assess the solid fraction that you get from your settings in order to be able to reproduce this and so on. So the alloy need to have in general a lower amount of silicon in order to get a good solidification range. We usually talk about under-eutectic alloys because that's the most common, but it's also possible to go on the over-eutectic side as well, but not so common. And then we get, as Anders explained earlier, we also have heat treatment possible, and also welding of different alloys. So here is a big change compared to conventional liquid high pressure die casting, I would say. Yeah. The tools or the dies, we use the same type of steel in the Rheocasting tool as we do in high pressure die casting. We have the same heat treatment to the steel and so on, so there's no difference here. Die tempering, I would say that is perhaps more important from a part geometry and what type of die lubrication you are using and so on, rather than the switch between the high pressure die casting into Rheocasting. In general, I would say that if we can be able to cast on a higher die temperature, it's beneficial for the process, but that's mainly decided by the geometry of the part. We are using the same spraying and release agents as we do for high pressure die casting. I would say that what you are choosing is component dependent as well. And as I said, a warmer die is preferable for Rheocasting. The big change in the die is the gatings and the casting systems. We are using larger gates. They are thicker. We try to prefer one flow so we can avoid metal meetings inside the cavity as long as it is possible. We also need larger overflows and vents, and especially also the thicknesses into these. It's very common that we need overflows where we have behind, for instance, a core or something that we get the metal meeting there. We would like to place an overflow so we can get out the metal that have met, so to say. So we have thick gates, which is more like permanent mold type of casting, so to say. If you would like to include squeeze pins, etc., that's also possible in the same way as it is for high pressure die casting. And as I said, vacuum, it has been proven to be beneficial for Rheocasting in the same way as it is for high pressure die casting. So, yeah. Take the next slide. And then if we look at this, we can come in from two two different routes from high pressure die casting, or let's say from more thin walled into Rheocasting, and then we have more from the permanent mold type of casting, low pressure, thick into Rheocasting. So, and there's slightly difference in how you approach these type of castings. So take the next one. If we take the thin wall into Rheocasting, it's more similar to conventional high pressure die casting design. Often it's very small or minor design changes that need to be converted. Alloy, however, needs to be changed, and there are alternative alloys that exist. We use normally larger gates and vent areas, which means that here you might have a change compared to in how you remove the gates and so on. You use perhaps conventional trim pressing and things like that. Perhaps that have to be changed into some kind of cutting solution instead. We have seen that since we are solidifying a majority of the material outside the cavity, we have less shrinkage forces inside the cavity, which means that we can use that as applying smaller drafts if needed compared to high pressure die casting. In these type of castings, I would say that vacuum is always preferable in order to get rid of the gas entrapped. Placement of venting and overflows needs to be analyzed with simulation due to the different flow behavior compared to high pressure die casting. We have seen that simulation is always something that is needed. We don't have the same experience in Rheocasting as we have in high pressure die casting, and therefore we need to build up, and then the simulation tool is a very good tool to establish this. And then we see velocities are higher, or depending on the geometry, and how high we can go. Limits are not yet really established, but velocities are, however, low in general compared to liquid casting. And as I said, simulations is a very good tool, and I would say always needed. And then if we look at the other type of castings where we come in from the more permanent mold, thick wall castings, the design here is different compared to thin wall, because we only have one source of pressure, which is the plunger, and we need them to see that the part can solidify towards the plunger, so we have more pressure roads open inside the casting, if I say. So you need to think a little bit more pressure with Rheocasting compared to perhaps speed as you normally think in liquid casting. So we need to ensure that we get the right solidification path towards the plunger. We don't have any external feeders that you have in permanent mold. We can use steel sliders instead of sand cores. We also have some possibilities for sand cores. We are in projects evaluating this at the moment for perhaps, I would say, impossible geometries, rather thinking like that. We believe that the gating in Rheocasting are anyhow smaller compared to permanent mold. Here it's important that we have a controlled velocity for flow front stability, because in these type of castings we see that we have a very laminar filling behavior, totally opposite from high pressure die casting, I would say. Overflows in somehow is very important in these type of castings, where we need to make sure that we get out the bad materials, let's say, or the first material, flow fronts and things like that. We see here also that we have an increased productivity compared to permanent mold, and basically we are actually introducing a totally new palette of business possible for high pressure die casting compared to what they can do today. And also here, I would say simulation is always needed. And then we come into training. We have a training program where we train operators in production, design and marketing and sales, and basically all the steps that we have inside from creating a casting. So, so we have different sections. We have the theory, how to make the slurry. We have practical slurry making and process settings, component development, alloys, what to think about alloys and things like that, benefits and why you should use Rheocasting and not conventional liquid casting. The market, what we see about the market and the different applications, and then the cost structure of Rheo components and so on, and then different applications and so on. So which is also included in when people invest in Rheocasting. So it's basically from all steps within an organization here. Yeah. And then we have the commercial aspect and the new segments. We see that we bring new market shares for high pressure die casting foundries by introducing Rheocasting with increased productivity. We can use already traditional permanent mold alloys like A356 with Rheocasting, and we can also introduce very low silicon alloys that can be cast with Rheocastings that introduce new business opportunities. Each die casting machine will also get a larger process window, meaning that each die casting machine is applicable for more part numbers compared to liquid casting. We see an increased die life with reduced heat checking, erosion and soldering and things like that. We can cast thinner and longer compared with high pressure die casting with alternative material that gives also improved properties. We see increased thermal conductivity with secondary alloys, which is very interesting for electronic applications that generate heats and telecom, for instance. We see big benefits with pressure tight and leak-free components, which we can cast without impregnation. And then we have heat treatable and weldable applications that is difficult with the conventional liquid casting. And then we claim that we give a more sustainable end product because with reduced silicon inside the component, it means a lower CO2 footprint compared to eutectic alloys. And then we can cast closer to the finished shape and give less scrap after machining. Yep. So thank you. This is a little bit from the foundry perspective of introducing the Rheocasting technology.
Thank you very much, Per, for this nice and fine presentation. We will soon go over to this interesting part of the webinar. We would like in these WebLearn webinars to give you the opportunity to discuss, of course, with the presenters, but also to hear from each other and your different experiences. So I will leave the word back to you, Anders, because I know that you have prepared some questions that could be interesting to discuss. And for all of you participants, please raise your hands, put on your camera, and or write something in the chat. And I will now also stop the recording. So feel free.